Greetings, chemists. This lecture will be on the topic of equilibrium. And we'll start off by talking about or expanding on an idea that was in the previous video on reaction rates. We had talked about the collision theory, which is that molecules had to get together and collide in order to form new molecules, and that this happened at a specific rate. We're going to continue the idea of rates in talking about the idea that reactions can actually go forward and backward. There are some reactions out there called reversible reactions. And a very famous example of this is a gas in our atmosphere called nitrogen dioxide, NO2. And it undergoes the following reaction where it turns into N2O4, dinitrogen tetroxide. And this is the gas in our atmosphere here that has that yellowish brown color. It's what smog is largely composed for. It's what gives smog its characteristic color. And if we balance it, it looks something like this. And from collision theory, this is actually very sort of easy to understand. You would have two NO2 gas. You would have an NO2 molecule and another NO2 molecule, and they would collide into each other at some speed, and that would be enough energy so that they form one N2O4 molecule. Okay? No problem. But what also happens is if you have N2O4 sitting around in the atmosphere, at some fraction of those molecules over time will actually spontaneously just fall apart and turn back into two NO2 molecules. So this reaction, we'll write it like this. It actually goes in both directions, that these things are constantly smacking into each other and turning into these guys, but these guys are also constantly decomposing and falling apart back into these guys, and that this happens simultaneously. So let's set out some general rules for reversible reactions, and let's take a look at. I'm going to make up. Let's say we had a beaker, and into it, in some water, we're going to put chemical A, like that. And let's suppose that chemical A does a similar reversible reaction, that it can spontaneously turn into chemical B, but that chemical B can also spontaneously turn into chemical A, and that this is a competing process. And I didn't really draw my beaker large enough, so I may have to we'll improvise here. Let's suppose I start with this many. Okay, I have all these molecules of A bouncing around in the beaker. These are each, kind of going their own way, and eventually they will collide, and eventually they will turn into some molecules B. So let's say this is my start. Okay, as I dump a bunch of A into the water and I let it float around. At a certain speed, these A's will turn into B's. Now I'm going to make these rates don't necessarily happen at the same amount. For instance, it might be that 3 moles of A per second will turn into B, but only 2 moles of B per second will turn into A, right? It could be a number of different rates, and that rate can actually change based on the concentration, the temperature, and everything else. So I'm going to make up some rules here. Let's suppose that for this reaction I've created, that 1/2 of all the A's at any given moment are going to try to react and turn into B's, okay? That's the rate of the forward reaction, the reaction in which A's turn into B's. Let's also suppose that 2/3, don't want to do 2/3. Let's suppose that 3/4 of all the B's in the solution will also simultaneously react and turn into A's. Okay? And that's constantly happening. So I'll show you what this looks like, and we'll do several iterations of it. So we start with this amount. Let's see what would happen if this was my starting amount and I followed these two reaction rates. Well, I know that half of my A's are going to turn into B's. So I have 1, 2, 3, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I meant to put 12 in there. Let's pretend I had just to make the math easy, let's pretend I started with 12. Okay, let's say there were 12 A's in there, and half of all of those are going to turn into B's. So what I'm going to wind up with is 6 of those A's are going to turn into 6 B's. Now, if I count up, 3/4 of my B's will have to turn into A's. Well, there aren't any B's in there now, so 0 B's are going to turn into A's. So we'll get 0 A's. All right, if that happens, let me go ahead and draw the new situation. I will have 6 A's have turned into B's, leaving 6 behind. None of go backwards, and so I would have A, B, A, B. I would have 6 of each at the end of that first time window, okay? All right. Now, we're at a new point in time. Let's say this is at time 1, okay? And let's say I wait another amount of time equal to that, and it happens again. What's going to happen? Well, now, based on our new concentration, half of my A's are going to turn into B's. Well, I have now 1, 2, 3, 4, 5. I have 6 A's. Half of that would be 3. So 3 A's will turn into 3 B's. What about here? 3/4 of my B's will turn back into A's, and now I do have some B's. All right, 1, 2, 3, 4, 5, 6. I should have gone. Now it turns out I should have gone with 2/3. All right, 6. What's 3/4 of 6? It's not going to be a round number, but we can round it off here. So 3 times 6 divided by 4, 4.5. I'll round that up to 5. So about 5 B's will turn back into A's. All right, so I'm going to lose 3 A's and gain 3 B's, but I'm going to lose 5 B's and gain 5 A's. What will be the total change? I think it's a net gain of 2 A's. So if I started with 6 A's, I'll now have 8. So I'll have 1, 2, 3, 4, 5, 6, 7, 8, and then I'll have 4 B's. 1, 2, 3, 4. So that's what my solution is going to look like now after one more movement. Okay, so this is now, I guess, time 2. And then it'll happen again. What have I got now? I've got 1, 2, 3, 4, 5, 6. I've got 8 A's, and half of those A's are going to turn into B's, so 4. So 4 A's turn into 4 B's. Now 3/4 of my B's are going to turn into A's. What have I got? 3/4. I have 4 B's. 3/4 of that would be 3. So 3 B's are going to turn into 3 A's. So that's a net movement. What happens? I gain 4 B's. I lose 3 B's. So I gain 1 extra B in this scenario. Okay. So I'm going to keep going here. Let's make a new beaker. In the new beaker, if I gain 1 B and lose 1 A, I will be at, well, let me draw a bigger beaker so I have room. That would be from 8 A's to 7. So I'll have A, and I should have 5 B's. 1, 2, 3, 4, 5. And this would be now at time 3. Now, what's going to happen here? I have 7 A's. If I take half of those are going to turn forward into B's. So half of 7 would be 3.5. I'll round it up to 4. So maybe 4 A's turn into B's. And of my B's, 1, 2, 3, 4, 5, I'm going to take 3/4. So 3 times 5 divided by 4, 3.75. I'll round it up to 4. 4 A's go to 4 B's, but then 4 B's are going to go to 4 A's like that. And notice that at this point, that actually doesn't change anything. That as many A's have turned into B's as B's have turned into A's. And so I'll still wind up with the same situation. Okay? So, what happened here? We started off with stuff moving very quickly, with 6 things changing at the very beginning. Then we went to a case where 3 and 5, right? That's a little slower, and then 4 and 3, and now 4 and 4 until we got to a spot where the actual change in concentration was not that much. In fact, it's nothing. And from this point on, this will continue to happen. So at some point where we reach a situation where the forward reaction, which is A turning into B, is happening at the exact same speed as the backward reaction of B turning into A. Once you get to that point, we have what we call a chemical equilibrium. And that's the definition of equilibrium. When the forward and reverse reactions occur at the same rate. And we can look at this solution. In this particular solution, A, there were 7 A's and 5 B's, and that's never going to change. There will always be a ratio of 7 to 5. Okay? So what we'll say is we could take the concentration of A and divide it by the concentration of B, and we would get some number. And that number is not actually dependent on how much we started with. It's not dependent on any other factor other than that forward and backward rate eventually coming to the same speed. And so what we do is we call this, we're going to say that divide out will come into some constant K. We'll call that K the equilibrium constant. Oops, I'm writing off the page. K is the equilibrium constant.